So I'm going to talk about Xray. And in brief, Xray basically provides data structures that let you do pretty high-level analysis of multidimensional data. And so there are two parts to this. One is the high-level analysis, and the second is the multidimensional data. So I'm going to talk about n-dimensional arrays, right? So pretty dense data sets. And by the end of this lesson, and there's a lot of material here, but my goal is really to help you understand what the basic data structures are, why they are useful, understand that you can read and write NetCDF files easily, which is something people in the geosciences like us use a lot, and also understand that there's a general big ecosystem that builds on top of Xray. So if you can understand Xray, you can unlock a lot of functionality that other people have written and built on Xray. So I'm going to start basically just jumping right in. So here are just a bunch of imports. So that should be pretty clear. And what I'm going to try to do is always type the command so that you can follow along. So first I'm going to load an easy tutorial data set. And so you'll see that the main import here is import Xray as XR. So that's a pretty common convention. And we're going to do .tutorial.load data set, and it's called air_temperature. And so it should run successfully. And so let's see what we have here, right? So I'm going to just do this. So you type ds and you run your cell. So what you see here is what's called a repr. So it's a representation of your Xray data set. And so what is a data set? And really what's in a data set is many data arrays, right? And so we'll get to these terms. And so you'll see all the way down here is a data variable called air. If you click on this thing, you'll see that there are a bunch of values, 241, 242, et cetera, et cetera. The other thing to note is there are three names here, time, lat, and lon. So it turns out those are dimensions, right? So we have a three-dimensional array. One dimension is lat for latitude, one for longitude, and the last one is time. If you click this thing, you'll see that there are a bunch of attributes. So there's long name. So this is 4 times daily air temperature at a sigma level 995. The units are in degrees Kelvin, so that makes sense. That's why we're seeing numbers of 240, right? Oops, I'm just going to scroll down. And now, basically, there's one data variable here. It's called air, right? And then there's 3 dimensions, and we'll see that also coordinate labels. So the latitude, for example, if you click here again, you'll see the values. They're going from 75 to 15. So this is going from 15 knot to 75 knot. If you look at longitude, you'll see it's going from 200 to 330. And if again you click on these thing, you'll see attributes. Okay, that's longitude in degrees east. All right, so that makes sense. And finally, we have time. And you click the values, you'll see that there are a bunch of these date time 64 things, which you maybe saw in your NumPy lecture last time. And so you see there are actual dates, right? So this is 2013, 1st of January at midnight, 6 hours later, et cetera, et cetera. So this is a pretty high level overview, right? So this DS thing has a bunch of data in it, and there are many different types. I've been using, kind of terminology like coordinates, dimensions, and data variables. And I think you'll see that all of you intuitively have an understanding of this. So how do I pull out this data, right? I have all these values here. How do I do that? So the way you do that is to remember that data sets are dictionary-like containers. And so they map a variable name like air to a data array, right? So it's like a key to value, which is what a dictionary is. So you do ds, and I know that the name is air. So I'm going to type that in. And look at that. So this is now a data array. And it's really all of these values. And then if you keep scrolling down, you'll see that it's come with its coordinates, so lat, lon, and time. And there are a bunch of attributes here, right? So those are the ones we saw earlier. And so, right, so this is a data array. You'll see that it's telling us that there are 3 dimensions, right? So time, lat, and lon, and there are values associated with those dimensions. A useful shortcut is instead of typing with the square bracket and quotes, you can use the dot notation. So you do ds.air and you'll get this thing. Um, okay, so this is a pretty high level overview, right? And so maybe it's a little confusing. So now we'll jump into what each part of this air data array is. So let's do, so the first thing that it has, what Xarray does is it takes your data and it adds a lot of metadata, right? None of us is ever looking at a list of numbers, right? At the very least, in our mind, we have, okay, I know that my first axis is time, my second axis is lon, and my third axis is latitude, right? And then we work from that. What Xarray does is it tries to take that information that you keep in your head all of the time and store it with the data, and then let you use that metadata to do useful things. So, for example, I have here a data array, and you can see that it's a NumPy array, and it has 3 dimensions. And so I can figure out what the names of these dimensions are by running that. And you see it's time, latitude, and longitude. Okay. And we know that time is not just 0, 1, 2, 3, 4. It's actual dates. So 2013 January 1, for example. And so you can do ds.air.coords, which tells you that, oh, there are a bunch of coordinate variables. These are latitude, longitude, and time, right? I'm sorry, it's a little repetitive, but I'm hoping that the concept sinks in. And let's say that we actually wanted to know what these longitude values are. You do ds.air.lon, right? So this is like accessing a data array. So you get back a data array, and it's got all of these values, right? And so what Xarray does is it says, instead of you having to remember that the first point on the longitude axis was 200 degrees east, it lets you use this information that is already stored in there to let you do things. And so I will demonstrate that soon. Okay, so here's another, so if you could pull out, this is an alternative way of extracting the same information that I did previously. So this is the same as ds.air.lon, or you can even just do ds.lon, right? So this is just like pulling data out. The last thing that you can do is Xarray can let you add arbitrary attributes. So again, this is the same idea that you don't just have data, you have metadata also, and you usually carry the metadata in your head, but it's usually nicer if you can put it with your data structure and carry it around. So in this case, you would look at attrs, and you'll get a dictionary, right? So this is a mapping from long name is 4x daily air temperature, units, degree Kelvin, et cetera, et cetera, et cetera. You can assign your own attributes. So in this case, I'm going to do, so this is a dictionary. So you can just add something. I'm going to change this and call it Oceanhackweek 2020. And then we'll look at what happened. So you scroll down and you'll see that, oh, I've added this. And these are arbitrary attributes. As long as you can write them to an HTTP file, you will be able to do so. So you can, add all kinds of information about I did so-and-so analysis to get to these values, and now I'm going to save it. And you don't have to remember that. You can look at your data set later at whatever attribute you added. I guess there's a question here. Can you give some examples of DIMs that aren't coordinates? I assume DIMs is a superset of coordinates. So this is getting into a slightly complicated answer. I think I'll answer that question after this tutorial, just because it gets a little complex. What he's getting at is, so here, for example, I said that, oh, I have all of this metadata like latitude, longitude, and time, and those are like axis labels. Let's say you had an error associated with each value here, right? So that's also useful metadata that you want to carry around. So technically, you can assign that in here. And I'll put in a link to the chat to some documentation that talks about that, but it's a little too complicated for the level I'm going for here. Okay, and now finally, remember, we have ds.air is a data array, and there's all these values here. So let's look at that, right? So you call it .data, and you'll see it says array, bunch of values. You scroll down, and it says D type is float32. So I'm hoping some of you at least recognize that this is a NumPy array, right? So the way you can run it is you do that. So this is an n-dimensional NumPy array that stores a bunch of values. Okay, so this is the data structure that is sitting at the bottom of Xarray in this case. There's a NumPy array. On top of that, you're adding levels of metadata. So one is saying, okay, I have this data. And then let's scroll back up. Actually, sorry, scrolling too much. Let's look at our data array again. And so you'll see that here you have this NumPy array, but then you go one level up, you've added the names for the dimensions. So it says, okay, here's a three-dimensional array of values. The first dimension is time, the second dimension is latitude, and the third dimension is longitude. And then you add another level of metadata, which is, okay, it's latitude, but those 25 values actually correspond to dimensional values here of 75 degrees north, 72.5 degrees north, so on and so forth, to 15 degrees north. Your longitude values, of which there are 53, going from 200 degrees east to 330 degrees east. And finally, you have 2,900 timestamps, and they're going from 2013, January 1 to 2014, December 31. All right, so for quick review, Xarray provides two main data structures. One is a data array that wraps an underlying data container. This is all very abstract, but you should really just think of it as an n-dimensional NumPy array and plus a bunch of associated metadata, right? And usually we don't just have, air temperature. Maybe you have also air pressure as a field that you want to work around. It's usually useful to have collections of data arrays, and so that's called a data set, okay? And so to review, the DS is a data set. In this case, it only has one data variable or data array. And then you can access that with ds.air, and that will give you access to these actual values and a bunch of metadata. Okay, I think I'll take a 30-second break and see if anyone has any questions on that bit. Okay, so first question is ds.data the same as ds.values? There is a very small technical difference. In this case, it is the same. Oh, sorry, ds.add.values is what we want. And so that's a NumPy array. Because in this case, the Xarray object is wrapping NumPy array, it's actually the same, but at the end, I have a short demo of different data structures that you can wrap. And in that case, it can be different. Next question, how is Xarray different from Pandas? Pandas works for two-dimensional data sets. So if you can think of your data set as an Excel sheet, use Pandas. If your data set is not an Excel sheet, use Xarray. Okay, someone is having trouble with the HTML bit. So the way to do that is, oops. So as long as you set that and then you do ds.error, you should see what I'm seeing. Hopefully that works. Okay, so yeah. Xarray basically began as a project by Stephen Hoyer, who is working with Pandas to basically make Pandas-like things for n-dimensional arrays, right? And so you will find that if you know Pandas, a lot of those concepts carry over. So in Pandas, these may be called index variables, and that's actually what Xarray calls them deep down, okay? Yes, Alex Kearney asks, oh, sorry, I'm getting distracted. Okay, so I assume everyone has a rough idea of what this is, right? So you have data and you have metadata, and the point of using Xarray is that you can use your metadata to do cool things, right? So I'm going to do a quick demo here, and we're going to visualize the first time step of our data, right? So I'm going to say, I'm going to plot some NumPy arrays, because that's how I assume a lot of you are familiar with. If you're coming from MATLAB background, something like this is probably familiar, right? So if I do lat, this is a bunch of values. If I do lon, it's a bunch of values. And let's pull out the first time step, which turns out, oops. And we can look at first, oh, total mess. So that's a NumPy array, right? And now I'm going to use matplotlib to make a plot. Let's see, we'll do, and this may work. It didn't work. Okay, it has some kind of complicated errors. So I promise, okay, so I had to put in a dot transpose here to get this to work. But does this make any sense to everyone? Like, what is going on here? Why do I have to transpose my data set, right? But let's keep that there. And let's try to do, oops, sorry. So that's, how I would make a plot. You could sit and play around with this to try to actually get the latitude on the y-axis. I don't actually remember how to do that right now for a good reason. So now let's go back. This is my air temperature data set. Sorry, dot data is a NumPy array. And if I wanted to take the mean, I would do something like this. And it's like a time mean. Really, is this clear what I did here? I took a mean along some axis. Do you know which axis I took a mean of, right? The only way you know that is if you know that the 0th axis is time, right? So this is an example of you keeping metadata in your head. And every time you read your code, you go back to your old notebook, you have to remember, all right, this is a time mean. And maybe if you're slightly fancier, you would do something like this. So it was easy for you to remember, right? Let's see how I would do the same thing in Xray, right? So I would take ds.air. This is my data array. I'm going to select the first time instant. So in this case, you'll see now I have a 2D array that's lat 25 ln 53. I've picked the first index 0. And then I'm going to just do plot. Now look at that. We know that this is a sensible figure that I got on my first attempt. You can see that it's put actual dimensional values 20 to 70. That's correct. You can see that it's used these attribute values to put nice labels like latitude, degrees north. So that tells you, right? You can see on the x-axis it's going from 200 to 330. So it's longitude, degree east, super useful. You can look at the color scale. You can see that it's labeled it with the units attribute again, degree Kelvin, and tells you that you're looking at air temperature at sigma level 995. All right. And let's say I want to take the time mean of something. I would do dot mean, give it time. And it'll give me back a thing with latitude and longitude, right? Because I've reduced over the time axis. And we can plot that. So now you'll have something that looks like a mean temperature over all the data set. And it's a latitude versus longitude. So this is kind of just a quick contrast. I'm sure some of you have done something that looks similar in either Python or MATLAB. The idea behind Xarray is because your data has metadata associated with it, we can use that to make our analysis really, really easy, right? So like this, take dot mean of time. And if I come back to this notebook in a month from now, I'll know that I took the mean along the time axis and I have a time mean field. Okay, there's a question about iCell and cell, and I'm going to get to that right now. So these are basically some examples for how you would pull data out of your Xarray object. And so there are two main ways of indexing, which is the term for pulling data out. This is called .cell and .icell. Cell uses what's called label-based indexing. So this is where you would use the latitude or longitude values, the dimensional values, right? So you would say, I want the value at 30 degrees north, and it will try and find that for you. The other way you can index is what's called position-based indexing, which is what you would usually do with something like NumPy or MATLAB, where you would say, oh, give me the first index or the 0th index or the 10th index. And what value that 10th index corresponds to, you have to look it up or you have to remember, right? And so let's see what this is. All right. Label-based indexing. So somebody asked about Pandas. So under the hood, Xarray actually inherits a lot of its rules from Pandas. And it, like I said, a main motivation for writing Xarray was to bring that ease of use and functionality to n-dimensional data sets. So in this case, my task is I want all of the points for 2013 May, right? So I would do, so 2013 May is kind of like a dimensional value, so I know I have to use cell. And I know I want it along the time dimension, and you would do 2013 May and run that. And so you'll see it's picked out 124. This used to be 2,920, so it's subsetted our data. And we can click on the time thing and look at the first value is 2013 May 1st. Looks good. Scroll all the way down. And you'll see 2013 May 31 at 6 p.m. Right? So it's pulled out all the values for May. And again, if you're familiar with Pandas, this should look pretty familiar. But yeah, so you get back the data, right? You can see it keeps all of the metadata that it can. All it's done is subset in time, and it's done it using these dimensional values that are easy to think of, right? Instead of you having to figure out, okay, May is really the 50th to 150th index or something like that, which is what you would do with NumPy. So this is an example of how Xray uses its metadata to make your analysis easy. You get told it, please select along dimension time, and then it's thought about it and said, okay, dimension time is the 0th dimension on this array, so I just need to subset that. And he said 2013 May, and then it looks at the values for time and picks out all the values that satisfy the condition, and then gives it back to you. And it's really quick. You can do usually, so that's one example. So let's say you wanted a range of values, right? So in this case, I would, it's called slicing, and you'll see why. So I'm going to say I want, I want to go from 2013 May to 2013 December. How about that? And you run that. And now you'll see you've got back 980. And we can check our values. The first value is May 1st, and the last value is December 31, right? So it subset your data in this pretty intuitive fashion. Usually when you need to do something like this, you'll have to remember that you need the slice operator, right? But again, I don't expect you to remember everything just because this is the first time you've seen it. One of the ideas of this notebook is as you're working on your projects and doing your analysis, you can come back, look here to see how to do common things. And at the end, I have links where you can go to for more documentation. So that's the time axis. Xray has very powerful time functionality, which it inherits from Pandas. But let's say we want to work with pulling values in longitude, right? So I'm going to say I want the 220.4 value, right? So this is 220.4 degrees east. I'm going to provide that, and it gives me an error. And so this is it's not good. It says key error. And so the reason is there is no value for 220.4, right? So the way we can check this is let's look at our values. And I'm looking for 220. So there's 215, 217.5, there's 220.0, and then 222.5, right? But there's nothing called 220.4. Common way is most of the time I just want the closest value, right? So I would tell it, okay, just find me the nearest one. That's fine. And so we do that, and it will find you a value. You'll see that you get a 2D data set, right? Latitude, time, no lon because you've only pulled out a single value that's at 220.0. So it looked through those values, figured out that 220 was the closest, and gave that back to you because that's what you asked for. There are more options. They're like method equals ffill, I think, which is basically, do you want the value to the left or the value to the right? Okay, so there are options that you can use to play with what you want. You can even tell it, find me the nearest value within a range of 0.1 degrees or something. And then if it can't find it, it will raise an error, or it will find you the one that's closest, right? So there's many options. You can look up docstring, right? So if you're familiar with notebooks, you can do something like that, and it'll tell you. So if you scroll down here, you'll see there are a bunch of options for method. I just demonstrated nearest, but you can find a couple of other options. There's tolerance, which is what you tell us, okay, I want it to be within 0.1. If not, give me an error because then I need to do something else. Okay, so that's nearest. And let's say we want to pull out a value at a bunch of points, right? So you can actually make this pretty complicated. 16 north and 32 north. And again, we'll do method equals nearest. And you'll see you gave it 2 latitude values, so you get back a array that has 2 values along lat, 15 and 32.5. So again, it's chosen the nearest ones. But then everything else should look kind of familiar to you, right? I hope at this point. Okay, so there's a question. Does nearest consider a given distance from it or choose the nearest no matter how far? So by default, it chooses no matter how far. If you want to give it a distance, then you would specify that tolerance argument. How does it handle nan? It really doesn't care. It just finds the nearest value and will give it to you back. If it's a nan, you will get a nan. Okay. Before that, Shikha Singh had a question about the format of the date. I was using 2013-May. The answer is it's very flexible. 2013-05 is almost certainly supported. So this is where Xarray builds on others' packages like Pandas, so we inherit all of the hard work that they've done. Okay, so .cell is label-based, and .icell is position-based. So here, for example, I'm just going to pull out the first value. The time equals 0 will just give me the first index, right? And so if you look at the time, that was 2013-01, right? So that's the first value. So this is entirely equivalent to doing ds.air 0, except with that, you have to remember that the first dimension is time. Here it's very clear. You said, give me the 0th index on the time axis, right? So it's much more readable and it's less for you to have to remember. Similarly, you can do slices. So in this case, let's say you wanted the first 10 values along latitude, you would do slice 10. And so you see you get 10 values. And then if I scroll down, you can look at the labels and they go from 75 to 52.5. Those turned out to be the first 10 along the latitude axis. Okay, so let me just quickly check the time. So I have like 15 minutes left, so this has gone pretty slowly. So maybe we'll treat the rest of this notebook as mostly kind of a demo, and you can try things out on your own and then ask questions, right? So we're going to do some small computations. The idea here is we want to calculate a grid cell area associated with this air temperature data, and we're going to use that to make kind of a weighted mean. But it's really nice because it demonstrates a lot of cool functionality that Xarray lets you do, right? And so this is what the formula is. It's kind of a constant times cosine of latitude, okay? And it's approximate, don't worry about it. The point of this is to demonstrate computational concepts. So what we're going to do is I'm going to pick this cosine latitude bit times the delta ln and do that. So delta ln, I'm assuming is, so that's in meters, right? And we can multiply this by cosine of latitude. So one cool feature is you can just pass this to NumPy functions and it will do the sensible thing. Oops. Okay, so this looks kind of weird because you have to remember that cosine expects radians while your data is in degrees. So you do that. Okay. I'm a little confused. Okay. Anyway, so here's what's happened, right? So you've taken ds.ln. We can multiply that by things, and things will work. You can take the cosine of that using the NumPy function, and you'll get back cosine. And again, I've multiplied. And so all of these operations have happened in a way that makes sense. And what you get back is still an Xarray data array, right? And because you gave it something that only has dimensions ln, you get back something that only has dimensions non. All right, so I'm going to save this as a variable dln. Yeah, so this is basically accounting for the, oh, this is my mistake. This needs to be lat. So this is basically accounting for the fact that longitudes get closer and closer as you go further north, right? That's basically what it's doing. And so if you look at DLON again, you'll see that I made a mistake earlier. I should have used lat. And so you get a value that a data array that has a single dimension, which is latitude. And now we basically make something similar for the spacing in latitude. So again, I'm going to use 110 kilometers. And so you'll see this function, ones underscore like ds.air.long. So let's look at that. So again, if you're familiar with NumPy, this should look familiar. What it does is it makes a data array of ones that looks like this lon variable, right? So now I'm getting a data array that has one dimension, lon, and has the appropriate coordinate labels. And so I'm going to multiply that by 111 E3, and so you get this, right? So hopefully that's clear. And now what we need to do is take the delta lon and the delta lat and multiply them together, but we need to be clever about it because we need a value for each grid cell, right? So you need to get back a 2D thing. So let's see what happens if you just do dlon times dlat. You'll see that you get back a 2 dimensions, right? And it's got latitude 25, longitude 53. So you've got a 2D variable. We can also visualize this. Again, as simple as doing dot plot. That looks kind of reasonable. As you go further north, the values get smaller. That looks okay. So let's see what's happened here. You've taken dlon, which has dimensions of latitude, right? So it has dimensions of latitude. And you have dlat that has dimensions of longitude. You multiplied them together, and it's given you a 2D variable. If you were doing this in NumPy, you may do something like dlon.data, blah, blah, et cetera, right? You have to remember to add a new axis. Okay, my first axis is latitude, my last axis is going to be longitude, then I'll do my multiplication. You'll learn about things like broadcasting, et cetera. What happens here is that Xarray is smart enough to realize you almost never want to multiply things that have 2 different dimensions together, right? It makes almost no sense to multiply the longitude dimension by the latitude dimension. Instead, you want to go for each longitude value, you do the multiplication. And so you really want to get this 2-dimensional array. And Xarray has thought about it and decided that, oh, these 2 dimensions are different. And so it basically does what's called automatic broadcasting. I think you saw this maybe in your NumPy lecture. What's happened here is very nicely shown in this image from this Jake van der Plas book. So here's how you would do something similar. So imagine that was your latitude axis. This was your longitude axis. And what it does is it expands the first vector to the right and the second vector downwards, multiplies the 2 to get the answer, right? And if you want to do this in NumPy, you have to do things like reshape, new axis, all kinds of things. Xarray will do that for you. As long as it knows that the 2 dimensions are different, it will not multiply them together. It will do this automatically. Okay. So hopefully that was clear again. I know this is a lot of material in a very short amount of time. So come back to this, click around, try things, and you should be able to learn. And now let's see if what I want to do now is a kind of very simple mean, right? Wait, let me go back. So we have dlon times dlat. So let's make a cell area, which is dlon times dlat. And again, this is a 2D variable. And what I'm trying to do now is wait, or just demonstrate multiplying by this kind of area, right? To do ds.air, I'll just take the first timestamp. And so you get a bunch of values, but what's happened here is Xarray has used the fact that, oh, the latitude variables on ds.air and the latitude variables on area are the same. And so it will line those 2 things up in space and then multiply them together sensibly, right? So you don't have to remember, oh, my latitude variable is decreasing on this first variable, but it's increasing on the second variable, right? Xarray will already line those things up for you because it knows where those data points are in space in terms of axis labels. So in this case, you got an answer. So let's, in this case, I'm going to create a copy. So I'm going to call it cell area bad. And the reason it's bad is I'm going to add a little bit of error, right? So we'll do, let's add, let's say 10 minus 4. It's a very small error. And you'll see this is a pretty good data set, data array, looks fine. It's got a bunch of values. You'll see that there is a little round off error here in the values. And now let's do that same multiplication I did earlier. Nope. Now this is important. So you'll see that you got nothing back. You have an empty array that has shape 0 along latitude, right? So this is very different from what happens when if I did cell area times this. So there you get 25 back and you get a bunch of values. So what's happened is the same thing. Xray has compared these values of lat. There's here it's 75.0001 and 75.0. Those are not the same, so it will not multiply them together automatically. So anytime you're doing an analysis, you see that you're losing data or you're getting extra nans. This is what's happening. It's that your coordinate points are not exactly lined up, and so Xray tries to not do anything because it's like, oh, these are not at the same point. I cannot multiply them together. So yeah, if you notice extra nans are missing points, it means they were not aligned exactly. Usually this means you have to go in and fix your values, right? And here's a little link to other things that you can do. Let's see. So I think I have 7 minutes. So these are kind of the very fundamental concepts that I was trying to get to you. One is that Xray has these high-level objects that add metadata to your data. The metadata lets you do analysis really easily and conveniently. So it means that you have to remember less about your data set. You can always do something like this, look at it and see, oh, that's right. This thing has dimensions named lat, lon, and time, right? And that these are these values. So this is the region that my data set covers. You can do things like pulling data out with .icell and .cell, and you can use those dimensional coordinate values to do that. The other thing that Xray does is broadcasting, right? So if you scroll back up, it does, where in NumPy, you have to be careful and reshape things properly so that they lined up. Xray is smart enough to realize that dimensions lon and lat are different. And so it will automatically do what's called broadcasting to get a two-dimensional result. So if you multiply something that has dimension lon by something that has dimension lat, you will get back something that has dimensions lon and lat, okay? The last main concept is what's called alignment, which is that Xray tries to put things on the same grid, and if things are not exactly lining up, it will either stick in a bunch of nans or you will lose a bunch of points, which is what happened here. It's like, oh, there is no intersection set to these points. I cannot do anything, and it gives you back an empty data set. So when you find this is happening, it means that your coordinates were not aligned exactly. In the beginning, it can be annoying, but I found that it really makes me be sure about what my data set represents when I'm working with it. So the rest of this is just going to be a quick demo about some kind of high-level computations. So again, this is very inspired by Pandas. So let's say a common thing we want to do is take something like a seasonal mean, right? So what you can think of that is a group by operation. So what it does is it creates 4 groups with these labels, DJF, JJA, MAM, SON. That should remind you of December, January, February, June, July, August, et cetera, et cetera. And so what it does is it takes all these values. It knows the time labels associated with the time vector. And it can use that information smartly to figure out, okay, these points are in this season, these points are in this season. And this is useful because taking a seasonal mean is basically just as easy as, so this option basically divides it up into groups. And then on each group, I want to take the mean and we'll give you back something that looks like this. So it's like latitude, longitude, and season, 4 seasons. So you've taken your data set and then reduced it now to seasonal means in basically 1 line, right? And then there are things like, here's how you would do monthly means. You would say dot resample, time equals capital M. And if you look at our time vector here, you'll see it's got labels 31st of January. Next one's 28th of February. The next one's 31st of March. So now you've taken those 2,920 points and reduced them down to 24 for 2 years, right? So this is all Pandas syntax. So if you go to our documentation, you'll see examples on how to do these things. And if you're coming from a Pandas background, they should look pretty familiar. Okay, I'm going to skip the weighted one just to go show you some plotting very quickly, because that's something else that I find I do often. So I'm going to call this seasonal mean. And so in this case, I'm going to do, let's look at what our seasonal mean thing is. It's a data set. So in this case, I want the air temperature. So I do .air. And now what I'm going to do is I'm going to make a plot. And I will say I want ln on the x-axis. The y-axis is time. And I have 4 seasons. And I'm going to put them on 4 different subplots, right? So there's going to be, in this case, I'm going to say column. So call for column equals season. Okay. And so if you look at it, you'll see that the x-axis share limits, they have nice labels. You'll have nice title labels. You'll see the seasons are out of order. It's kind of annoyance, but you can see what it's done here. And they all share the same color bar that's shown here, right? And so let's look at our seasonal mean object. You'll see that everything that I told it are basically dimensions, right? So there's some flexibility here, but for the simplest possible case, I told it put the ln dimension on the x-axis, put the lat dimension on the y-axis, and then in columns, give me seasons, right? You can kind of go pretty crazy. We let you do a lot of things. So here, for example, you can do, I want a contour plot. So you do .plot.contour. Again, seasons are columns. You can give it the number of levels, color bar, et cetera, et cetera. You can even make line plots. I was just trying to demonstrate things, right? So now in this case, I took the mean on longitude and I made this line plot where each season is given a different color and the y-axis is latitude. X-axis is air temperature. Okay, 1 minute left. So my last quick demo is you do all this high-level analysis, right? Which is all great and super easy, but at some point you need to write your values to disk so then you can come back to it. Super easy. It's 2 netcdf. Okay, in this case, it's giving me a little bit of complaints. I'm not sure why, but yeah, 2 netcdf with the file name will write out a fully CF compliant data set, or at least mostly CF compliant data set that is super easy to read. So in this case, I wrote a file called my example dataset. I can read this as open dataset, my example dataset. And you get something. Let's just look at that. It really should look the same as this DS that we wrote to file. The way you can check is just doing that, and it says true. So I wrote DS to file, I read it from file, and I get exactly the same thing, including all metadata, all the attributes, everything. So netcdf is pretty well supported. We also support a bunch of other file formats. You can click there to see things. Again, here are many useful links for our documentation. So things like what are the terminology we use? How do you create a data array? Say you have an existing NumPy array or something like that. How do you create a data array? You go here. If you want how to do X, you can click there and you'll see a list. It's like, whoops. How do you add a data array to your data set, et cetera. So this is, on the left side, you have, here's a task you want to do. On the right side, here are functions that may help you do what you want to do, right? So you can scroll down and find that. We have some tutorial stuff that's up there. And the last part of this notebook that I don't have time to demonstrate is how Xarray really ties into the rest of the ecosystem. So here, for example, you can convert to a Pandas data frame. You can convert from the data frame to Xarray. In this case, you were just working with NumPy arrays, but really you can wrap things like Dask, which I think some of you may work with, which lets you parallelize things. So Xarray can wrap a Dask array. You can also wrap a sparse array. You can wrap GPU arrays. You can also wrap pint arrays, which add units to your computations. If you multiply something Celsius by Kelvin, it will throw an error saying, this is crazy, don't do this, right? Or if you try to add those two. So yeah, it's very flexible. And if you scroll down, you'll find a little more advanced functionality if you're interested. But fundamentally, you just need to know that Xarray provides data structures for high-level analysis of multidimensional data. The two key things are multi-dimensions. So if you have 2 dimensions, stick with Pandas. If you have more than that, use Xarray. And high level means we try to let you use your metadata in your data analysis. So I'll stop there. Thanks. Thanks to the organizers for inviting me. It was good fun.